The fifth problem, prove that circle drawn on the equal sides of an isosceles triangle as diameters pass through the midpoint of the third side. Given AB is the diameter of the circle and point P is a point on the semicircle, angle BPA is equal to 90 degree. Similarly, given AC is the diameter of the circle and P is a point on the semicircle, angle APC is equal to 90 degree. Therefore, triangle APB and ACP is right angle triangles. In the question given, the triangle ABC is isosceles triangle. Therefore, AB is equal to AC, opposite sides of equal angle in isosceles triangle. So we have AB is equal to AC. Now we can write AB square is equal to AP square plus PB square, and AC square is equal to AP square plus PC square. Since AB is equal to AC, we can say that AB square equal to AC square, which implies these two equations are equal, that is AP square plus PB square, that is AB square, which is equal to AP square plus PC square, which implies here AP square and AP square can be cancelled. So we have PB square equal to PC square, which implies PB is equal to PC. That is, P is the midpoint of BC. Hence the proof. Prove that all the circles drawn on the four sides of a rhombus as diameters pass through a common point. Let ABCD is the name of the rhombus. Since ABCD, AC and BD are the diagonals of the rhombus, then AC and BD, being the diagonals of rhombus, bisect each other at right angles. Therefore, we get ACBD bisect each other at right angle. So, these angles should be 90 degree. Let's see the circle where AB is the diagonal. Here we got this angle is 90 degree, which implies O is a point on the semicircle. Therefore, O is a point on the circle. Angle AOB equal to 90 degree, which implies O must be lie on the circle having AB as its diameter. If we consider this circle, the diameter is BC, then here the angle is 90 degrees, so O must be a point on the circle where BC is the diameter of the circle. Also, we can say that O must be a point. O must be a point on the circle where DC is the diameter. Also, O must be a point on the circle where AD is the diameter. Therefore, we can write angle BOC equal to 90 degree, which implies O must be lie on the circle having BC as its diameter. O must lie on the circle having DA as its diameter. The point O is common to all four circles. Hence the proof. Picture below, a triangle is drawn joining the ends of the diameter of a circle and another point on the semicircle, and then semicircles on the other sides of the triangle as diameters. Prove that blue and red crescents in the second picture is equal to the area of the triangle. That is, we have to prove the area of the blue crescent and the red crescent, which is equal to the area of the triangle. So we have given a triangle. Let the sides of the triangle as A, B and C, and since this triangle is in the semicircle, here C is the diameter. Let A and B are other sides of the triangle. We know area of the circle is pi r square, that is area is equal to pi r square. R is d by 2, then we can write pi d by 2 all square, that is pi into d square by 4. Area of semicircle is pi into d square by 4 into 1 by 2, that is half of area of the circle. So we get pi d square divided by 4 into 2, that is 8. So area of the semicircle is pi d square by 8. Area of the circle is pi r square. So area of the semicircle is pi r square divided by 2. Now using diameter instead of radius, we have area of the semicircle is pi d square by 8. So here we can see that triangle is a right angle triangles. Therefore, c square equal to a square plus b square. Let's have the areas of the semicircle of diagonal A. So area of the semicircle with diagonal A, we can write it as SA. So area of semicircle with the diameter D is equal to A is, let's denote the semicircle's area as SA, which is equal to pi a square divided by 8. Now area of semicircle with diameter D is equal to B, with diameter D is equal to B, denote as SB. Now we can add. So look at this picture. Now we can add the area of this semicircle and area of the semicircle and area of this triangle. We area of semicircle with diagonal A plus area of semicircle with diagonal B plus area of the triangle. Before that, let AT is the area of the triangle, then which is equal to the area of the semicircle with the diagonal C and area of the blue crescent and area of red crescent. So area of crescents blue and red plus area of the semicircle which is SC, we can write it as SC. So we have SA plus SB is SC. So SC plus area of the triangle equal to area of crescents plus SC. SC is common, so we can cancel each other. So we have area of the triangle is equal to area of the crescent. So area of the blue and red crescents is equal to area of the triangle. So the answer.